We will continue our discussions of helicopter in forward flight. In the previous several presentations, we have looked at how much is the inflow through the rotor. We developed a very simple model by Glover. We also talked about the various coordinate systems we could use, a shaft plane or a hub-based coordinate system, or a tip path plane-based coordinate system, or a no feathering plane coordinate system. So all of these are common. And once you have chosen a coordinate system, we know in that coordinate system the blade is going to be flapping up and down. If it is not a tip path plane coordinate system, but in the tip path plane coordinate system, it will only have a steady coning angle. There is no flapping up or down. Likewise, because of the pilot's control actions, the blade is going to be pitching up and down as it goes around the azimuth. Again, if it is a no feathering plane, you will only see a collective pitch. That means a time invariant pitch that is seen by all the blades all around the azimuth. So we have some information now available. So now we are ready to tackle the problem of how much lift is being generated by the whole rotor. A rotor is made of a number of blades. So each blade is divided into small blade elements like we used to do in the past. Then we need to take each blade element, which is a cross-section of an airfoil, plus a small amount of span-wise width or the radial width, delta R. So we need to know how much lift is being produced, how much forces, drag is being produced, and perhaps at moments on that airfoil. So one of the first things we need to do is we need to find the conditions of the airfoil, because we need airfoil aerodynamics in our work. We need to know what is the angle of attack experienced by the airfoils on the blades as the blades spin around all the way for various sections, all the way from the root to the tip. So this is what we are looking at in this particular set of slides. So let's go to the next slide. So what are the things that the angle of attack of the blade section depends on? The pilot is putting in both a collective pitch, that means all the blades are rotating by the same amount, pitching up or down. If theta naught is positive, it's pitching up, rotating upwards, away from the rotor disc. If theta naught is negative, it is going downwards. The blades may have some geometric twist, so we are assuming it's a linear twist measured from the root. So this is the theta naught. This is the extra amount for the twist. Normally the twist will be negative, so that it goes negative from root to tip. Less and less pitch angle is generated. In this coil system, theta naught is in radians, theta twist is also in radians. This is the linear variation times R over R. This is the pilot when he or she tilts the swash plate front or back. They are producing theta 1s. When the pilot is tilting the swash plate left to the pilot's left or right, they are producing a theta 1c. So this is the first thing that we see is the blade is rotated relative to the plane of rotation, or whatever plane we are dealing with, a tip path plane or shaft plane or no feathering plane. Of course, in the no feathering plane, theta 1c and theta 1s will go away. We will only see these three terms. But in the other planes, whether it's a shaft plane or whether it's a tip path plane, all the components here will be seen. So these components, these are pretty obvious, but we also have other things to consider, which is the relative velocity that the airfoil sees, because the free stream is coming at an angle, alpha. We are also introducing some induced inflow. The blade is flapping up and down, so it sees the air coming towards it or away from it when it's flapping up or down, so that need to be considered. Then there are some effects which we call unhedral and dihedral effects due to the coning of the blades. So we are going to look at these three bullet items one by one, because the first two bullets are kind of pretty straightforward. Then we had to combine them, all of them, to come up with the angle of attack. So that's what we are going to be doing in this particular module. So let's look at the blade flapping effect. Let's say the blade is flapping upwards at an angular velocity of d beta dt, which we call beta dot. That's the angular velocity. Then r times d beta dt is the linear velocity of the blade section. So this section is moving upwards at this velocity. So this aerofoil thinks I am standing still. Air is coming towards me from the top to bottom at r times d beta dt. So anytime something is coming from up to down, we call it a downwash. So we are seeing a downwash of magnitude r times d beta dt. So when we say beta dot, we are talking about the time derivative of the beta, which is the flapping angle, and the time derivative of that with respect to time. Now let's look at what are the other things we need to consider. So the free stream is coming this way from left to right. This is caused by the vehicle forward velocity, which is v infinity. The disk is tilted at an angle alpha. So this angle is alpha. Therefore, if you draw a line parallel to the disk, this angle is alpha because these two lines are parallel, these two dotted lines. So the blue line makes an included angle alpha with respect to either the rotor disk or this blue dotted line here. So this component of velocity is called the edgewise component of velocity parallel to the rotor disk. So that component is going to be v infinity times cosine of alpha. But we also get a normal component, which is called v infinity times sine of alpha. Then we have the Glover induced inflow velocity, capital V, and small lowercase v. So we get a total additional downwash of v infinity sine alpha plus v. How about in this direction? In this direction, the blade is spinning forward, omega r. Then it sees this edgewise velocity, which is v infinity cosine alpha, times sine of psi. Why do we multiply by sine of psi? Because when the blade is to the pilot's right, psi is 90 degrees, sine of psi is 1, so we are adding the free stream velocity, which is coming towards the blade, with the forward motion of the blade. So this is the total velocity the blade says. When the blade is in the 270 degrees, sine of 270 degrees is minus 1. So this becomes negative, omega r minus v infinity cosine alpha. That means the blade is moving away from the oncoming airstream, so the airstream is chasing it. So this is the relative velocity, is omega r minus v infinity cosine alpha. Therefore, by putting in this sine of psi, we are able to take into consideration this relative velocity as we go around the azimuth. So this component is sometimes called a ut or u tangential in the plane of rotation. Whichever disk we call it, this is the rotor disk. Finally, the unhedral dihedral effect. So again, this is a blade at psi equal to 180 in front of the pilot. This is behind the pilot at psi equal to 0 over the tail boom. So air hits the blade this way. So this is the blade in front of the pilot at psi equal to 180. It sees this air is made of two components. One is perpendicular to the blade this way. So it's v infinity sine beta. This acts like an upwash, okay? Upward directed, because there's an airfoil here. The airfoil sees the air coming up this way. It also sees a radial component of velocity, which is going this way. So this velocity vector can be decomposed into this component, v infinity sine beta, and v infinity cosine beta. This cosine alpha is approximated to be 1 because alpha is a small number. If you're using a more comprehensive program such as a CIMRAD or RCAS or UMARC or DIMOR, they won't make this approximation. They will, wherever v infinity is, it will be v infinity times cosine of alpha. How about on the psi equal to 0? The same v infinity cosine alpha, or v infinity approximately, has got a downwash. So the air is going from above the rotor disk into the rotor disk, Here it is going from below the rotor disc up into the rotor disc. So we see a sign here, it is plus. Here it is minus. So depending on the azimuth angle, the sign is changing. So to account for it, you can multiply this by cosine of psi. So when psi equal to 0, we get minus of V infinity sine beta. When psi is equal to 180, cosine of 180 is minus 1. So this becomes plus V infinity sine beta. So this is called a upwash or a downwash, depending on whether you're up here or down here. So this is another component that we need to consider. So adding them all up and together, we get the free stream component of velocity, which we saw here, plus the induced velocity V. That's the second term. The third term is a flapping dynamics term, R beta dot, downwash. The last term is the unhedral term. So all of them are written as a downwash component. So this is UT, this is UP. So this angle we sometimes call it phi. So theta minus phi. Phi is arctan of UP over UT. Now, except near very close to the root, as you go outboards, UT is pretty large. For example, for a Black Hawk helicopter, omega R near the tip is around 600 feet per second, a little bit over that. That means even in the midspan, this component is like a 300 feet per second, hundreds of feet per second. This is tens of feet per second. Therefore, tan inverse of a small number is that number itself in radians. So we can write alpha as approximately as theta minus UP over UT. So in exact programs such as CFT, CAMRAD, RCAS, DIMOR, UMARC, HOST, you name it, they would compute this exactly. But if you are doing a spreadsheet-based assignment, like you may do in a homework problem, a Georgia Tech helicopter aerodynamics class, you'll make this approximation and write it this way. So again, UP is this number, UT is this number. Okay. So we can solve for the alpha. So every radial location, if you know something about the pilot control theta, which we don't know yet, assuming theta is known, and if you know something about the blade flapping dynamics, which we don't know 100% yet, we can solve for the alpha. So normally in a spreadsheet program or a MATLAB program or analytical integration, this alpha is very, very small. So normally cosine of alpha, cosine of beta, cosine of theta will be 1. Likewise, theta is also a small angle in radians. So sine of alpha will be alpha, sine of beta will be beta, sine of theta will be theta. So this is common in spreadsheet-based approximations or analytical integrations. Whereas if you're doing a CFT code or one of the comprehensive analysis, no need to make these small angle of attack assumptions. Okay, we have found the alpha effective. So this is the theta. So it requires us knowledge of theta naught, which we don't know yet. Theta 1c we don't know yet. Theta 1s we don't know yet. We just leave them here. These are pilot's actions. Pilot will control the blades by using the tilting of the Schwarz plate or moving the Schwarz plate up and down to change the theta naught, to produce the extra thrust, and also to rotate the rotor disc front to back or laterally, as we have discussed before. This is UP. So by the way, lambda is the total inflow, which is this quantity, divided by omega capital R. Okay. Omega times the tip speed. So V infinity sine alpha plus V divided by omega capital R is called lambda. So we can think of it as lambda, omega R times lambda. Then we have all the other terms as we shown below. So in small angle of attack assumption, if we invoke it, cosine alpha S will become just a 1. Sine beta will become just remain as beta. cosine psi will remain as it is. Okay. So if you are using a shaft plane, for example, you will use a lambda shaft. Okay. If you are using a tip path plane, it will become a lambda TPP. Of course, beta dot will go away in tip path plane. So depending on the coordinate system, we'll put a subscript to tell which coordinate system we are finding the inflow. Why? Because this alpha depends on the coordinate system that we are using. Now, the numerator is a ut theta minus up. So this is ut times a theta minus up. Now, this has got a beta dot. Beta dot is d beta dt. So you could write it as d beta d psi times d psi dt. D psi dt is the angular velocity in radians per second times d beta d psi. Beta is sinusoidal function beta naught plus beta 1s times sine of psi plus beta 1c times cosine of psi. So when you take a derivative of sine of psi, you'll pick up a cosine of psi. When you take a derivative of cosine of psi, you'll get a minus sine of psi. So this is the beta dot. So we can throw this expression in here. Then you can do a longhand multiplication, substitute for this, and group the terms carefully. After some little bit of algebra, nothing fancy. You could use a symbolic math program such as Maple or Mathematica if you wish. Or you can just take a long piece of paper and write it up, all of these things. Then you'll get this expression. And when we notice that these two numbers appear in pair, and then these two appear in pair, which is the same as here, these two appear in pair, which is same as this. We saw earlier that this is an included angle between the tip path plane and a no feathering plane when viewing the helicopter from the pilot's left. Okay, so helicopter is going from your left to right. You're looking at the helicopter. So this is the included angle between the tip path plane and the no feathering plane. If you're looking from the back, this would be the included angle between the no feathering plane and the tip path plane. So anyways, this included angle is independent because regardless of the coordinate system in which it's measured, this would be the same included angle because the angle between two lines. So it's a fix. So beta has got the same significance as alpha, theta, because these things appear in angle of attack. So 1 degree of pitching has got the same effect on this term, and therefore on alpha has 1 degree of flapping. So sometimes we say 1 degree of pitching is equivalent to 1 degree of flapping for this reason. So we have computed this quantity which appeared in the numerator of expression here. We can divide it by ut. So by the way, before we proceed further, we see that V infinity is written here as alpha tip path plane. Where did this alpha tip path plane come from? Because up to here we didn't have any alpha tip path plane. We just had a V infinity times we had a lambda which had a V infinity sine alpha. So what happened? Why did we get an alpha tip path plane all of a sudden? So what happens is, if you look at it, let's say you're in the shaft plane. So this angle is called alpha shaft. This angle is beta 1c. So alpha shaft plus beta 1c is alpha tip path plane. So when we do this algebra, when you combine things together, you'll get a alpha s plus beta 1c combined together. That's why we call it alpha tip path plane. Fine. So this is the alpha effective. So comprehensive programs at every radial location, assuming the pilot angle action is known, they will compute this explicitly. So once you have the alpha effective, now it is time to compute the lift coefficient, drag coefficient, and pitching moment coefficient. Remember from our 2D aerofoil theory, we know that a CL is a function of alpha, but also local Mach number. CD is a function of alpha, also local Mach number, Reynolds number. And the pitching moment at the quarter chord point is a function of alpha and potentially Mach number if we include compressibility effects. So the lift coefficient, drag coefficient, and pitching moment coefficients can be done in a number of ways. In comprehensive programs such as Camera 2, RCAS, DYMO, UMARC, they will use a table lookup of CL, CD, pitching moment, CMC over C versus alpha, and also it's a function of Mach number. So it will be a two-dimensional table. For every Mach number, for every alpha, you can find the CL, CD, CM from that particular table. That table is commonly called a C81 table. But if this table will be just a static data, just like in a wind tunnel, you test a CL versus alpha. For every alpha, you get a 1 CL at a given Mach number. But we know the flow is unsteady, so you have alpha is changing with time. So it's possible to use a small angle of attack unsteady aerodynamics, so-called the Theodosian theory, to correct for unsteady aerodynamics. What does this account for? Let's say you pitch the angle of attack by 1 degree abruptly. The lift does not instantaneously increase. It takes a finite amount of time because it takes roughly 6 chord lengths of travel before that full effect of that 1 degree is felt in the CL. So the unsteady aerodynamics accounts for the delay in the buildup of lift and also the buildup of CM pitching moment because of the time delay that takes place because the wake has to convect past the aerofoil. Then if you go to extremely high alpha, the blade has stall. When you pitch down, the blade is attaching. It may not go on the same path. So you may have a loop, hysteresis loop, where initially CL versus alpha follows along one curve. When you're pitching down, CL versus alpha follows along a different curve. That's so-called a dynamic stall. So comprehensive programs will have a dynamic stall corrections. There are a number of models, such as Peters model, Wanera model, other models, that are available. Leishman-Beddoes model, and so forth. Also, if the leading edge is swept back, then the wind is coming at the leading edge, not perpendicular leading edge, but at an angle. Then you have to correct for the sweep. For example, the Black Hawk helicopter, as well as the Apache, has got a leading edge swept near the tip. So we need to make some corrections for it. So these are normally accounted for. The textbook by Wayne Johnson and also by Gordon Leishman. Other books give you some information on how to correct it. We will, as time allows, we may look at it at a future time, but for the time being, we say that a CL and CD and pitching moment have been corrected for all these effects. It's very important we correct for these because, for example, dynamic stall will account for a very rapid rise in lift followed by the very rapid drop in the lift at the blade section. So this change in the abrupt changes in the lift gets transmitted to the hub, producing the vehicle vibrations. So if you want to get the vibration levels correctly, it's very important you can take into consideration dynamic stall effects, unsteady aero effects, compressibility effects, and of course, to a smaller extent, the sweep corrections. If you are using a spreadsheet model or a simple analytical integration, it's common to use a linear curve with C equal to some lift curve slope times alpha. If you don't know the lift curve slope, you'll just take it as 2 pi. If the airfoil is cambered, you'll use alpha minus alpha naught, where alpha naught is the angle of zero lift. And it's also common practice to assume the drag to be a constant, some nominal constant, and the pitching moment at the quarter chord to be a nominally a constant value. Again, more sophisticated calculations will use C81 tables with corrections for the local sweep angle, unsteady aerodynamics, dynamic stall effects, and Mach number effects. One poor man correction you could do it is you can compute the UT and UP and find the Mach number, either using the total velocity vector or just using UT because UT is much larger than UP. Then once you have the Mach number, you can take the incompressible CL, which you compute here, divided by the local Mach number that produce a rough correction of the lift coefficient for compressibility Fx. That's called a Prandtl-Glover rule. Notice that V infinity cosine alpha is the edgewise velocity. So when the blade is at 90 degrees azimuth, when the blade is moving up, you'll see two effects. One is V omega r, so the blade is moving forward. The wind is coming towards it at a velocity V infinity of cosine alpha, so these two things add up. That's all psi equal to 90 degrees. On the other side, the blade is moving away from the air, so the air is chasing, so you get omega r minus air velocity. That's why we can put a sine psi to account for the azimuthal variation. Therefore, you get a lot of dynamic pressure on the advancing side, very low dynamic pressure on the retreating side, as we have discussed it in previous presentations. Once you have found the CL, CD, and CM, you can compute the lift is 1/2 rho U squared. U squared is UT squared plus UP squared times chord times CL. This is the lift per foot of span. This lift, by the way, if you use a analytical curve fit, CL will become A times alpha effective, where alpha effective is as shown earlier. So you can again take a UT here, UT theta minus UP by UT. And then if you neglect UP squared as a small number compared to UT squared, you'll only have a UT squared. So the one UT in the denominator will be cancelled out, leaving only one UT up here. So we get this. Now we notice that you have a sinusoidally varying quantity, a sinusoidally varying quantity, a sinusoidally varying quantity. So when you multiply three sinusoidally varying quantities, you can get a sine, so not sine of psi, but sine squared of psi, but sine cube of psi. So you're going to get at least three harmonics, even with a simplified two-dimensional aerodynamics model. If you use a dynamic stall, other corrections, you may get higher harmonics from this lift. These harmonic variations or vibratory variations in the lift get transmitted to the hub. That's why the helicopters shake a lot. All right. So this is how L prime is computed at each radial location. So first thing we will do is, assuming you know how theta varies, assuming we know how beta is varying, we're going to address it in a follow-on presentation. You can find a sectional CL, CD, CM, and we can compute a sectional lift. By the way, you can also compute the sectional drag. They will be pointing along this total direction. So they'll be perpendicular to this direction and along this direction. So you have to rotate it normal to the plane of rotation, normal to this line and along this line. Okay. This red line is actually parallel to this line here. It doesn't quite look like it, but that's what it is. So we are going to stop at this point, this particular video.